Welcome to the valve cam mechanism example using SimXpert2010. In this tutorial you'll learn how to create motion parts automatically from CAD geometry, define contact between motion parts, and how to create a spring damper with the specified preload, stiffness and damping. This example will show you how to simulate a cam and valve train assembly. The example covers importing geometry, defining multiple types of constraints and defining contact. Firstly, we shall be working in the motion workspace. The first thing that you will notice is a large arrow in the model display window. This arrow indicates the direction of gravity. Gravity will not be taken into account for this tutorial. Thus you can hide the arrow by right-clicking on it and selecting Hide. Now click on Tools, Options, and CAD Import under the geometry tree. Check to see if the Create a Part for each body button is checked. This is needed when importing a sub-assembly and a parasolid, as SimXpert will otherwise create a single part from the assembly. Now import the mechanism geometry by clicking File, Import, Parasolid, and select the valve train.xmt.txt file. Click Open. Notice how each geometry is listed in the model browser. Motion parts need to be created from these geometries. Under Components, select From Geometry. A list of the geometry components is now displayed. Now double-click under the name list on the first item and change the name to Shaft. Do this for all 10 geometries and name them as shown here. Now we must choose which geometries are grounded. These geometries are the shaft, the block, the guide, the seat, and the cam. Select these geometries under the ground part list, then click OK. On the bottom right you will receive a message. Part mass properties could not be updated. Geometry is not a solid. This is due to the fact that the lobe and roller are not solid objects, but only surfaces. As a force rotation will be applied to the lobe, while the roller will only undergo translational displacement, there is no need for the inertias to be calculated, hence the warning can be ignored. Notice the component list, which has been created in the model browser. Closing the tree for each component will make the navigation of the model browser easier. Now we will begin assigning boundary conditions to the various components. The Connections tab houses various options for various boundary conditions. Under Connectors, select the Translational Boundary Condition. Use the box zoom tool to zoom to the rod and block, and select the rod for part 1 and the block for part 2. For location 1 under Method, select Geometry. For the feature, select one of the curved edges of the block as shown. This locates the joint at the curve's arc center. Under Orientation 1, select Method Z-axis only. Select Geometry as the axis method. Click on the feature field and select one of the straight edges as shown. This indicates the direction of the translational displacement. Click Apply. Now click Fill on the View Manipulation toolbar. Use the box zoom tool again to zoom to the area shown. For part 1, select the valve, and for part 2, select the guide. Click in the feature field under location 1. Select the edges filter and select the curve edge on the guide. Click in the feature field under axis. Select the edges filter and select the straight edge as shown. Click OK. Notice both connector boundary conditions are displayed in the model browser window. Now we will create the rotation boundary conditions. Under Connections, select Revolute. Click Fill in the View Manipulation toolbar and use the box zoom tool again to zoom to the area shown. For part 1, select the rocker, and part 2, select the shaft. Click in the feature field under location 1. Select the Edges filter and select the curve edge on the shaft. Choose Global for the method under Orientation 1. Click Apply, then zoom to the area shown. For part 1, select the rod. For part 2, select the roller. Click on the feature field under location 1 and select the edges filter. Then select the curve shown. Leave the orientation 1 method on global. Click Apply. Now hold down the right mouse button and drag the view over the cam and lobe. Select the cam for part 1 and the lobe for part 2. Click on the feature field under location 1 and select the edges filter. Then select the curve on the shaft as shown. Leave the orientation 1 method on global and click OK. There should now be 5 connectors in the model browser window. Notice the different icons for the Revolute and translational connectors. Please note, the global orientation was used for these joints, which align the axis of rotation with the global Z axis. If necessary, other orientations could have been chosen. Now we will define the contact boundary conditions. Under the Contacts tab, select the Curve option. Zoom onto the area shown. Under Curve 1 for part, select the roller. Click on the Features field and select the Faces filter. Select the roller. Under Curve 2 for part, select the lobe. Again, ensure the Faces filter is enabled under Features and select the lobe again. Notice that 2 edges will be selected as the lobe is an elliptical shape. Change the points per curve values to 10 and 20 respectively. And click OK. Notice the curve 1 entity in the contacts tree in the model browser. Now select the body boundary condition under Contacts. Zoom to the area as shown and select the rock as part 1 and the rod as part 2. The bodies are automatically assigned. Click Apply. Zoom to the section as shown and select the rock as part 1 and the valve as part 2. Click OK and notice the body contact entities in the model browser. Now to add a spring force in order to avoid liftoff on the roller and lobe contact, select the translational spring damper under the Forces tab. Zoom to the selected area and select the valve for the part under First Part. Select Geometry for the method and use the Edges filter under Feature to select the curve on the valve as shown. Now orientate your view so the top side of the guide can be seen. Select the guide as the part under Second Part. For the method, select Geometry. And for the feature, select the Edges filter and select the round curve as shown. Now ensure that the stiffness option is checked. Change the method to preload and the value to 1 Newton. Change the stiffness rate to 2000 Newton per millimeter. Ensure that the damping option is checked and change the damping rate to 0.01 Newton second per millimeter. Then click OK. Notice that a spring has been created but does not display correctly in our model. To correct this, double click on the translational spring damper entity. Select Visualization and change the values as shown. Then click OK. We will now add motion to the assembly. Under Motions, select Joint Motion. For the joint name, select Connector 5. Change the motion type to velocity. Now to specify velocity, in the expression field enter 720d. The value entered here indicates how many radians per second the lobe will rotate at. The default unit for angles in SimXpert is radians. Thus the D ensures that 720 degrees per second is used instead of 720 radians per second. Click OK to assign the motion. Now the model is complete and is ready to be run. Under the Simulation tab, select Simulation. Change the end time to 1 second and number of steps to 100. click the Start the Model Simulation button and wait for the simulation to complete. This is a complex simulation and might take some time. When the simulation is complete, click on the Results tab and select Animation. Press play to view the animation. Change the view to top to obtain a better perspective of the animation. Stop the animation and close the window. Now click on Chart under Results. Click on Simulation 1 Run and select the component which you are interested in. Here I've chosen the valve. Selecting Y as a quantity plots the Y position of the valve versus time. Click Add Chart to view the chart. To return to the model, close the window and select Window, Main Window. This concludes the example of the valve cam mechanism. Thank you for completing this tutorial. This tutorial was brought to you by Engineering Technology for Better Business.